Character Awareness in a Direct Output High-Rank Language Model by Maddie, Wang, and Zhang. So language modeling is an important task in natural language processing. We can use it in machine translation, dialogue generation, etc. And the problem is that state-of-the-art models still use simple word-level embeddings. These state-of-the-art models include mixture of softmax or direct output connection. And so what we're trying to do is create a character-aware neural language model that encodes subword information or creates more expressive embeddings through a CNN highway layer. And this feeds into a state-of-the-art direct output connection model. To do so, we'll train on data including Honey, Humans in New York, blog posts, and Penn Tree Bank.
Our approach is a custom architecture combining character-level CNN outputs and feeding it into the AWD state-of-the-art direct output connections model. Essentially, word-level embeddings, which are simple, performs poorly sometimes because of their bias towards word frequency. Replacing word embeddings with character-level generated CNN embeddings can feed subword information to fix this bias towards word frequency, which can improve performance of state-of-the-art language models. So on the right, you notice that we feed character-level inputs into the convolutional layer, max-fold over time, finally connected to a highway network, and these would output the word-level embeddings we now feed into our state-of-the-art language model, AWD LSTM DOC times 5. We use 3 LSTM layers instead of the 2 shown in a diagram, and these layers are connected to the final layer with direct output connections, which combines probability distributions from both the final layers and also from the middle layers in order to raise the rank of the final output matrix to improve performance. DOC is a type of MOS, and both of these are rank-raising techniques used in current state-of-the-art models. So what are baselines? We have 4 baselines. We have a 5-gram model, a simple RNN LSTM model implemented in PyTorch, a character CNN model, as well as the state-of-the-art model. Here are our test data results on Tree Bank and Pony. Our custom architecture performed better than the character CNN without direct output connections, but did not beat the state-of-the-art direct output connections model. One constraint we faced was in the number of GPUs we were able to employ, which meant we weren't able to train for a large number of epochs or use a large number of batch sizes. On Honey, state-of-the-art architecture performed more poorly than we expected, perhaps because the DOC architecture isn't meant for smaller corpuses. Next, in our analysis, we noticed that these are things that improve performance on our custom architecture. Adding direct output connections and increasing the number of direct output connections meant better performance. We also lowered learning rate, increased the highway dropout, and used large corpuses to perform better on the CNN and AWD. We noticed that training errors were higher for longer words, and that our character CNN were more sensitive to words with hyphens, which is shown on the figure on the right in orange, which is it's a PCA figure of n-gram representations of words, and we can notice that our representations are particularly sensitive to hyphenated words, which reflected the observations in ChemAL 2015.
In conclusion, we found that increasing the number of shortcut connections directly increased performance in char CNN-based language models. Additionally, we found that our custom architecture has potential in a setting with more memory resources. And we also found that subword information like including hyphenation can help with the performance in these complex architectures. For future experiments, we're hoping to experiment with a larger batch or a number of DOCs with more GPUs. And lastly, we hope to substitute DOC with MOS to reduce the number of memory or parameter demands.
We would like to thank our mentor, Xiaoxu, for help for the project. Thank you for listening.